So we are now going to implement this energy criteria very cleverly. Now think about it that as before, we'll say that one particular molecule is moving, which is the A molecule or B molecule, doesn't matter. And there is a second molecule which is sitting here. And when it comes here, so this guy is suppose moving, and this is static. And when it comes here, it will be something like this. So there will be a collision. Let me just draw it slightly in a bigger way. Something like this. And this is basically the center of the second molecule, which is static because we are talking about relative velocities. Now the question is, when it make this impact, how much energy actually is transferred? Doing a bad drawing. Okay, let's just stick to that. Okay, so the question is, how much energy is transferred along this line of center? That is more important. So if you have a head-on collision, so all the energies are transferred along the line which is joining the centers. But here, if we have a slightly off center, so then all the energies will not be transferred. Only the part of the energy will be transferred. So that we have to calculate. Now, how to calculate that? For that, we are saying that, okay, fine, there is a V relative along this direction. And suppose it is making an angle alpha with respect to the second molecule. And which means that along, if this is alpha, the component of the velocity along this will be nothing but this I'm calling as VLC. LC means it is basically line of center. So VLC means actually the component of the velocity along the line of center, means line joining the two centers. Line of center means a line joining the two centers. So there actually the energy will be transferred. So we're writing in terms of velocity, but we can easily convert it to energy. That we already know. And then we can ask this question, okay, fine, what will be the energy transferred along this line of center? And that will be nothing but half mv square, but instead of m we have to write mu because it's a reduced mass system. So only one particle is moving, other one is static. And then we have to write the v relative. Now you see here, so this is the v relative. So the component along this line of center will be nothing but, so this VLC, which is nothing but v relative into cos alpha. So this will be v relative square into cos square alpha. Now cos square alpha, I can easily write it as v relative square. I can write it as sine square alpha. Now the sine square alpha, now the question is, how will I write it? Now think about it. If I just ask, what is this distance? This distance is nothing but RA plus RB, the joining line of the two centers. So this is nothing but B max. And this I'm calling as B. So B is a variable. B is the basically center to center parallel distance. But then that B can be maximum to B max. So if this is B max, you can see from this triangle, you can easily see this triangle. So this thing is B max, this thing is B, and this angle is alpha. So I can easily say what is sine alpha. Sine alpha will be nothing but B by B max. So sine square alpha, instead of that, I'm writing as V relative square into, so sorry, it will be 1 minus sine square alpha. It will be 1 minus B by B max. So it will be B square by B max squared. So that is basically the energy transferred along the line of center. That should be greater than some threshold energy, otherwise the reaction will not happen. That we are making an condition, and that's why you are imposing it. Okay, fine. Let us assume that this energy transferred along the line of center should be more than epsilon star, which is the threshold energy. Now we have done a very simple calculation here that alpha can be 0 for head-on collision, as you can see, and then for grazing collision the alpha will be 90 degree. If you remember, this head-on collision means this is just directly coming, and the second particle center is also like that. There alpha is 0, and the other extreme could be this particle is moving and the second particle is just lying here. So this alpha in this case is 90 degree or pi by 2. So varying the b means actually varying the alpha, but we are just using the b language. They're all connected. Now the question is, so earlier we saw that this pi b max square, it has a dimension of cross section, because if you think that what is b max, there was one molecule which is suppose hitting another molecule which is bigger molecule or smaller molecule. So we can think of these are the two molecules, and we said that one is say Ra, one is Rb, Ra plus Rb is b max, and we said that if you think of this cross sectional area, so within this area, whichever molecule's center will lie within this area, those molecules will be hit by the molecule which is actually moving at the center. So this molecule which is moving around it, it has a zone, cross-sectional area. So that area is nothing but pi b max square. That area, since it's a value of dimension of area, so we call it as sigma. So this pi b max square sometimes is written as sigma. But right now we made a criteria that this sigma has to be greater or equal to something, so that we'll see. So this sigma is nothing but pi b square, or before we go to the definition of sigma, let us just look at only this part. So this part basically tells that I have half mu, before we proceed, this half mu v relative, this thing, this also is a dimension of energy, because half mv square is kinetic energy. So instead of half mu v relative, we could write it is basically the relative kinetic energy. So what we got is this line of control, the energy transferred along the line of control should be, it's like this, 1 minus b square by b max squared, and that should be greater than epsilon star. Or we can just rearrange it. You can say that, you can easily figure out that this b square by b max squared should be less than equal to 1 minus epsilon star by epsilon relative. You can easily figure out that. So you just put this epsilon relative here, and then bring this back here, and this bring this b max on the other side. You can easily figure out it is the less than sign. Now this is the criteria. So what it means is that, think about it. So we can just write it in other way, like we can just write it as or let me just use this space. So what I'm saying here, b square has to be less than b max squared into 1 minus epsilon star by epsilon relative. So think about it, like this b square, if the epsilon star is 0, which means actually there is no activation energy, then it will be all the criteria we have is just this b star will just have to be less than b has to be just less than b max. So any collision will give me reaction. So b goes from 0 to up to b max, and all this collision will give me reaction. However, if we make this choice that no, actually there is an epsilon star, which is actually pretty high, a pretty non-zero value. Of course, you have to have a criteria that epsilon relative energy, if this is less than epsilon star, then no reaction will happen, because think about it, if then actually this factor will be more than 1, and then actually it will be a negative number, which doesn't make sense, because what I'm going to do is that I'm going to multiply both sides by pi, which is an area, but then area is becoming negative, which doesn't make sense. So those reactions will not happen. So epsilon relative has to be greater than epsilon star. Now if epsilon star has a value, then it says fine, suppose it is epsilon star by epsilon relative is 0.5, then I'll get 1 minus 0.5 is 0.5. And then what I'm saying is that this reaction probability is not exactly, the cross section is not the exactly pi b max, it is slightly less than the pi b max, it is half of that area, which means that in the earlier case what we are saying that there is a effective cross section that we already wrote, and all the collisions, if they hit it, then the cross section will be nothing but pi b max squared. However, we are now saying that no, all cross sections will not give you a reaction, only a fraction of this cross section will give me a reaction. Which fraction? Say for example only this area, which we are drawing like this. A smaller area is giving me a reaction, that the smaller thing is coming from this factor right now. So I have very cleverly changed the cross section, we have reduced the cross section in the sense that only those reactions will be possible if it is less than say a particular, or the relative energy is more than the epsilon star. Now suppose if epsilon relative energy is just equal to epsilon star, so this factor will be 1, so 1 minus 1 will be 0, so the cross section we are seeing is 0, so we are saying that only the head-on collisions will give me reactions. That is the meaning of that. So this cross section we are calling is at the reactive cross section. This is not simply pi b max square, it is pi b square, but this b square is now connected. I mean, it has a criteria that it has to be less than equal to that. So the reaction probability will be nothing but, or the rate will be thermally averaged rate constant, will be nothing but this reactive cross section, as we have seen, times the relative velocity, and then we have to take the average, but we have not taken average on relative velocity because we'll do the averaging now. And then we are basically saying okay fine, and let's take an average over all the, basically we are integrating, and we are saying that all these energies will give me a reaction, that will be the total rate constant. However, only when this relative energy has a minimum value of epsilon star and it is going to infinity. So that integral just we have to solve right now. So we know that this sigma r is nothing but pi b max squared, as you can see here. Where is it? It is here, pi b max squared into 1 minus epsilon star by epsilon relative, and then it is multiplied by v relative, but I cannot write v relative because I'm integrating in the energy frame. So we can easily say that you already know this thing, it is half mu v square is epsilon relative. So v is nothing but twice epsilon relative divided by mu and square root of that. So you'll write it, it is twice epsilon relative, or we write it slightly differently, 2 by mu square root of that, and epsilon relative to the power half. And then I have g epsilon d epsilon, which is the distribution function. So this is basically sigma r, this is the relative velocity expression. And then I have, if you remember, this distribution which we just got, this distribution. So it is 2 pi 1 by pi kbt raised to 3 by 2 e to the power minus epsilon by kbt epsilon to the power half d epsilon. So let us write it. So it is nothing but, there are some constant, we can write it at the beginning, 2 pi times 1 by pi kBt raised to the power 3 by 2, and then e to the power minus epsilon by kBt, epsilon to the power half. These are all relative epsilon, d epsilon. So that is the expression for g epsilon d epsilon. So let us now calculate it. So the lower limit is epsilon star, the upper limit is infinity. Now see this, look at this integral very carefully. So what we have is pi b max squared, but that is also a constant that we can also take it out of the integral. So 2 pi 1 by pi kBt raised to the power 3 by 2 into pi b max squared. Inside integral, let us see, this I can write it as epsilon relative minus epsilon star divided by epsilon relative. But then I also have one epsilon relative to the power half and epsilon relative to the power half. Those will give me epsilon relative. So that will cancel with this epsilon relative. So I'm not writing that. And then I have 2 by mu, square root of that. And inside I have e to the power minus epsilon. This should be epsilon relative because I'm writing the distribution function also in the relative coordinate by kBt d epsilon relative. Now we have to somehow use the gamma function, but we cannot use because the lower limit is epsilon star. And also the variable here is epsilon relative. Now we can make a trick. We write it, okay fine, let us say that I'll just write it a new parameter, which is epsilon prime, which is basically epsilon relative minus epsilon star. So then d epsilon prime will be nothing but d epsilon relative. Why? Because this is a constant. This is a particular fixed energy above which this reaction is happening. So this integration I can just rewrite, only this integral part. I'm not writing the in between whatever we had. So that I can write very cleverly as E relative minus epsilon star times e to the power minus E relative minus E star into d E relative. So basically I'm writing it as into d E relative minus E star, because we know that d epsilon star is this is nothing but d epsilon star, which is d epsilon relative, is the same. But now look at it, what I have done in this process, I have actually multiplied this as an extra factor, which is e to the power plus epsilon star by kBt. I have put it inside a bracket. So then, which means that's why it is a minus sign. So I have to also multiply by e to the power minus epsilon star by kBt. Then I can integrate it. This is the value of the this is the integration, and then I can actually switch to epsilon star, and we know that if E relative, the lower limit is epsilon star, then epsilon prime actually goes to 0. So in that relative thing, if I just write it, then the lower limit will be now 0 in the next step, and when E relative goes to infinity, epsilon prime also goes to infinity. Now I have actually 0 to infinity limit, and then I can write this integral once again. So k of t will be nothing but, let us first write the constant, all these constants. So it will be 2 pi times 1 by pi kBt raised to the power 3 by 2. Then I have pi b max squared times 2 by mu, square root of that. And then let us see, now this factor is a constant because epsilon star is also a constant. So I'll have e to the power minus epsilon star by kBt into integral. I'm now writing the variable as epsilon prime, so I can write it as epsilon relative minus epsilon star. I can write it as epsilon prime, epsilon prime, and e to the power minus epsilon prime by kbt d epsilon prime, and the limits will be now 0 to infinity. Now this is a gamma function of the form of x e to the power minus ax dx that we can easily evaluate. So it is x to the power n minus 1. So x is nothing but x to the power 2 minus 1. X to the power 1 is x to the power 2 minus 1. So it will be gamma 2 by a to the power 2. And here a is 1 by kbt, remember. So the value of the integral will be gamma 2 is nothing but 1 gamma 1, which is just 1. And it will be just a square. So we can write away, evaluate. So it is 2 pi 1 by pi kbt raised to the power 3 by 2. Then I have pi b max squared 2 by mu to the power half e to the power minus epsilon star by kbt times this value of this integral will be it is 1 over a to the power a square. So the a was 1 by kbt, that squared. So it is nothing but kbt squared. It will be kbt squared. Now let us simplify what we have. So what you can see here, we have 2 here, 2 to the power half, and let us just work out with the 1 by 1. So this term and this term I'll not touch. I'll just arrange with all other things. So what we are getting, kbt square, and here kbt at the denominator to the power 3 by 2. So the square thing we can think of as it is 4 by 2. So I'll have kbt to the power half. And then think about the pi. Now I have a pi here, I have a pi here. So I'm not touching the pi b max squared, so that will just keep intact. So pi is basically, it is pi to the power 2 by 2, and this is pi to the power 3 by 2. So I'll have in the denominator pi to the power half. Then I have 2 here, I have 2 here. So 2 means actually 2 to the power 2 by 2, and it is 2 to the power 1 by 2. So I'll have 2 to the power 3 by 2, which is 19 but 8 to the power half. So because 2 cube is 8. And then I also have a mu here. So I have basically mu to the power half. So this thing is nothing but 8 kbt by pi mu, which is nothing but v relative average. So what do we get? So all these terms actually rearrange to give you a v relative average, and what we get is pi b max squared times v relative average. I did not write all the other terms, and times I'll have e to the power minus epsilon star by kbt. So now this is a modified expression for the rate constant, and we see the beauty here. So the earlier expression had only this part, pi b max square into v relative, and now we have actually e to the power minus epsilon star by kbt. Now this is a very beautiful result, because what we exactly was looking for, we got it, because it shows the Arrhenius-like behavior, and we got it from just by using the fact that this impact parameter, it is connecting to the impact parameter, that this ratio of this impact parameter to the maximum impact parameter will actually be connected to this threshold energy. And from that we got that, okay, fine, this we got back, by the way, the old cross section, which is the overall cross section, and then there is a relative velocity, but then it is saying that, okay, fine, so all collisions will probably happen, grazing to head-on collision. However, with a condition that all the conditions are now here, sitting here in that Boltzmann factor, that the energy has to be above a threshold energy, which is epsilon star. Thus, we see that even a very simple model, which is the collision theory model, that gives a very much Arrhenius-like expression, which we got, and then this simple collision model, which we did not get, where we did not impose the energy criteria. So A is nothing but your pi B max squared into V relative average. Now you see that A has a temperature dependence because V relative goes as square root of temperature. So the temperature dependence is not only coming from the exponential part, it is also there. So the pre-exponential factor is also temperature dependent. Now when you calculate, or when you we'll give you some problem sets where you will be asked to use this formula and calculate the rate constant for a reaction, for which actually you already know the rate constant. Using the three values, you can actually first get the old collision theory, which is nothing but this sigma, if we call this as a sigma, and times the V relative, and this is the old thing, and this the modified thing, we got an expression like V relative into e to the power minus epsilon star by kBt. So moment you include this factor, you'll see the number of collisions that is giving the reaction will be rate. So the rate constant which you calculate using this formula will give you a very high number, which is not a true number. Rate constant which you get using this formula will be more closer to it will be a lower number, which will be more close. But still, the actual rate constant which you get experimentally will still be much lower than this calculated rate constant. The reason is there is also an orientational factor that we did not discuss. Suppose, what do you mean by that? Suppose a collision is happening with some particular energy, and we know that from this expression that this will be a reactive collision. However, these molecules are not hard sphere. They also have particular structure, and this particular atom should come closer together. So by that, what I mean, suppose if this is perfectly oriented, like say I have some group here and I have some group here. So if I have a head-on collision, these two will react together to give me a reaction. But suppose now I'm having a collision like this, and then although these two hard spheres collide, these two groups are not actually coming in contact with each other. However, if I had rotated it in the sense that they're still colliding, and they're slightly far apart, but when they collide, these two groups will come in contact, and then the reaction will happen. So then it means that the proper orientation is also very important, or the three-dimensional orientation is very very important. So people actually to get to a current or get a better experiment or a better result, sometimes they just write they just compare these two values and they write it, okay fine, actually we'll get the true value if we multiply it with some other factor, which is sometimes called P, which is known as probability factor, times this modified rate constant, which is sigma into V relative into e to the power minus epsilon star by kBt, and this probability factor will always be less than 1. If it happens that okay, these molecules are actually behaving like hard spheres, then this probability factor is equal to 1, and whatever we just derived, that expression is perfect. But in reality, actually molecules have particular shape, and this reactive ends has to come closer together through a proper orientation. Then actually the rate constant which you are calculating is giving you an upper limit, so the actual rate constant will be slightly lower. So it will be not only that collision with a particular energy, but also it needs the right orientation, and that orientation you can compare with the experimental value, and you'll find that there is also another factor which is less than 1 that actually will bring down the calculated rate constant to the experimentally observed rate constant. So to summarize, actually what we discussed in this lecture is that we first talked about kinetic theory of gases, And then we talked about in detail the Maxwell-Boltzmann distribution of molecular speed, and then we used it to give the expression for the rate constant by collision theory. And we showed how basically one can use very cleverly the impact parameter and connect it to the threshold energy to get Arrhenius-like rate expression. And we showed that we can actually calculate this A, or the pre-exponential factor in Arrhenius equation, and we can get an expression where this thing also comes up. And that was our entire goal in reaction dynamics, which we showed that by using all this development, you can actually calculate the rate constant using just classical mechanics. Thank you.